Okay, so hello. Our new topic is weak and strong forms. So, what is a strong form? Maybe it's better to understand how we formulate a mathematical problem by using mathematics. And of course, the simplest case may be the things that we did in strength of materials. So remember that in strength of materials and in statics, we mainly deal with the equilibrium of forces or equilibrium of external loads. In other words, an object is in static equilibrium if the sum of the forces acting on the body is equal to 0. Now, if we exclude the dynamic problem, certainly this is the case. In case of a dynamic problem, certainly the sum of the external loads or forces has to be equal to mass times acceleration. Now, let's consider one-dimensional problem and how we can derive an expression for a one-dimensional problem. So this is the thing. And in fact, the easiest thing might be a one-dimensional axially loaded elastic bar. So what's an elastic bar? In fact, we know that the elastic bar can deform, and if you unload it, if you remove the loads, it will return back to its original shape. This is what we call elastic. In case of a one-dimensional elastic bar, certainly the load is in the direction of the axis of the bar. The bar may have variable cross-section, as you see in the figure on the left-hand side. And certainly there may be distributed loads along the bar, which is the function of the coordinate. Of course, we assume that the horizontal axis or there is an x coordinate which is attached to the axis of the bar. Certainly we put it at the left hand side, the origin of the coordinate, and we call it x is equal to 0 there, and x is equal to L on the right hand side of the bar. And at an arbitrary cross section, the area is also a function of the coordinate. Certainly there is a distributed load. This distributed load can be also a function of the coordinate. We have an external load, T bar here. Now, we will write the equilibrium and how we can derive the differential equation which represents this problem, this physical problem. So in this case, what we do is we just take a tiny slice at an arbitrary location x, and we write the forces acting on it. Now, in fact, at an arbitrary location x, there is a stress, and we always say that stress is outwards. So it's in the normal direction of the surface if you cut it, and it's outwards. Simple. And let's say that this infinitely small slice has a thickness of delta x. Therefore, at the right hand side, the stress will be, or force acting on the surface will be P x plus delta x. Now, we are talking about the deformable objects. And indeed, the displacement on the left-hand side is ux, and on the right-hand side, it is ux plus delta x. Certainly, the displacement is also a function of coordinate. Now, we have a distributed load. Since we have a tiny slice, we can assume that within this tiny slice, this distributed load is located at the center, and it's constant. So it is b x plus delta x divided by 2, since the thickness is delta x. That's okay. Now let's write the equilibrium condition. Now remember that P is the normal force. Therefore, I assume that it is always towards the outside of the slice that I cut. So on the left-hand side, it is minus px plus body force B bx plus delta x divided by 2. This is, and it acts along the thickness, so I assume that it's constant along the thickness, so it is delta x. This is the distributed load plus p x plus delta x, and it has to be equal to 0. So this is the force equilibrium for my tiny slice. Now, if I divide this expression with delta x, this is what I'm going to get. This will be the expression. So it is px plus delta x minus px divided by delta x plus bx plus delta x divided by 2. Now, here is the critical point. Now, remember what the definition of the derivative is. Simply, I take the limit of this expression while delta x goes to 0. So it is, just a moment, please. Okay, when delta x goes to 0, this becomes b of x, as you see here. And this becomes the derivative of p with respect to x, this expression. This expression will become the derivative of x with respect to x. So, as a result, I will obtain this equation. dp dx, so derivative of p with respect to x plus bx is equal to 0. Now remember that p is the normal force. Of course, I can write it by means of stress. So in this case, if I solve this expression, I will find the normal forces if Bx is given. Now, we know that the stress is defined as force divided by the area. Force acting on the surface divided by the area. So at an arbitrary cross section, it is Px divided by A of x, and that's equal to sigma x. Sigma is the stress here. Okay, so Px is equal to A of x multiplied by stress value. Now, we have another definition. Remember that we measure the deformation by means of strain. We use strain because it's non-dimensional. It is independent of the geometry. And remember that the strain is defined as elongation divided by the original length. Now let's look at our tiny slice. So on one side, on the right hand side, the deformation is ux plus delta x, and on the left hand side it is u of x. Therefore, the total elongation will be the difference of these two displacements. So this will be the total elongation of this of my tiny slice, And remember that the original thickness is delta x. Now, again, as delta x goes to 0, the strain can be written as du dx. Okay, so this is another expression that we have. Therefore, the strain is the derivative of displacement with respect to x, as we see. Now, I can write the relationship between the stress and strain. According to the Hooke's law, for a linear elastic material, stress is equal to Young modulus, or modulus of elasticity, multiplied by the strain. So the relationship between the strain and stress is linear. Okay, now let me combine all of these into the force equilibrium. So first of all, AX divided by sigma x. Now remember that AX, if I substitute this into this expression, it is d over dx, A divided by sigma x. Now I can do another thing. I will put the stress into this expression here. Okay. And then I will put this expression into here. So as a result, force is equal to area multiplied by the Young modulus multiplied by the strain. Of course, I will have the definition of the strain du dx. So it is A multiplied by E du dx. If I substitute it here, I will obtain this expression. So d over dx, derivative of A multiplied by E du dx, plus B will be my equilibrium equation. And this expression is valid between the values of x between 0 and L. Certainly, I have boundary conditions. So remember that I have a traction force here. T is denoted, T bar is traction force. And that has to be equal to, or traction in other words, that has to be equal to the stress at x equal to 0. So it is E du dx at x equal to 0, and that is equal to P0 divided by A0, and that is equal to minus T due to the definition of P, because P is always towards the outside of the normal, and outside the normal vector in this case is towards the left. This is my normal vector for this phase, and my normal vector on the right hand side is towards the right. Okay, so this is minus T. So sigma is equal to minus T bar. And in fact, on the right hand side, the displacement is prescribed, U bar, and I can easily say that UL is equal to U bar. Now, I find my strong form. Basically, strong form is this set of equations or expressions. This is the strong form of axially loaded elastic bar. Okay. So where else? Of course, this is for the elastic problem, and this is not the only problem that we are dealing with. Certainly, we are dealing with heat conduction problem. We want to define the heat distribution in a wall, for example, in a building. We do the same thing, more or less the same thing, or same thing in mathematical manner. So the point is this. So the total heat flux is heat flux multiplied by the area which is coming in, and the total heat flux is heat flux multiplied by the area, which is heat flux going out. Now what we do is the same. Basically, we just take the whole thickness. Certainly, we have the siding, building paper, furring strips, concrete blocks, some other insulations, or many other things. Paint, and so on, so on. So maybe some space, doesn't matter. What we do is simply we just look at the overall thickness. In this case, the overall thickness is L. And we just take a tiny slice again, which has a thickness of delta X. And we magnify it. So then we write the equilibrium equations for this tiny slice. So the heat coming in is Qx multiplied by Ax. Heat going out is Qx multiplied Qx plus delta X plus multiplied by Ax plus delta X, because this tiny slice has a thickness of delta X. And certainly we have the heat generated inside this tiny slice. And we say that it is S of X plus delta X divided by 2. And it is inside the thickness. If we write the conservation of energy, in this case, heat flow in minus heat flow out, which is the total accumulated heat inside this small unit. And then we have the heat generated. So remember that we assume that the heat generated through the thickness is constant. So it is Sx plus delta X divided by 2 multiplied by delta X. Again, I will do the same thing. I will divide the whole expression by delta X. Then I will arrive this expression. So this is Qx plus delta X, Ax plus delta X minus Qx, A of X, delta X, and that's equal to heat generated Sx plus delta X divided by 2. This is the conservation of energy. And from here, as in the limiting case, if I take the delta X to the 0 in the limiting case, I will be left with this expression. So derivative of Q multiplied by A. Q is the heat flux, A is the area. So the area may change. Again, dx, that's equal to S. Now, what else? We have the Fourier law. So remember that Fourier law gives us the relationship between the change in temperature and the heat flux. So it is minus K dt dx. Here K is the conduction coefficient, heat conduction coefficient. Then if I substitute this expression into here, then I will arrive this equation. So d over dx, a k dt dx plus s is equal to 0. So remember that on the left hand side, the heat flux coming in is prescribed, it's given. So it's minus q again because of the direction. That is equal to k dt dx, and that's equal to q bar at x equal to 0. And on the left hand side, on the right hand side, sorry, the temperature is given because normally in our rooms we want certain temperature. For example, in winter we want the room temperature to be between 21 and 23 Celsius, whereas in summer it is between 24 and 27 Celsius. So we have the boundary conditions. temperature in the room is given as T bar at X is equal to L. And finally, these expressions, all of these expressions forms the strong form of the heat conduction equation in one dimension. Okay, so what else? Sometimes we deal with the diffusion. So what is the diffusion? That's the point. Now, just imagine that you have a needle and then injector full of ink. Okay, and then the diameter of the needle is infinitely small, very small, very small, and you just put the needle inside the water, inside a glass of the water, and just put a tiny droplet, very small one, and yet immediately you pull the injector outside the glass. Okay, and begin to watch the glass. What you're going to see is immediately that ink will begin to spread with an equal speed in all directions. And as you see that, as the ink spreads, the color is getting lighter. So what it means, certainly the ink is made of some small particles. Just imagine that they are infinitely small particles. And the total quantity of the particles that you inject into the glass of water is constant. And in time, as you see that, the intensity is decreasing. As a result, it's getting lighter. Its color is getting lighter. What it means, so the concentration is getting lower and lower because the same amount of thing, in this case, ink, is occupying a larger area. It can be a population. So just think that you put 100 people in 100 meter square room. Simple. So each you have one person per meter square, and then just take these 100 people and put it into the 1000 meter square room. So what you're going to get is then you have one person in 10 meter square area. You have the same amount of people, but certainly you see that the intensity is getting lower. So that is what we call concentration. Simply, in this case, the concentration is denoted by C, as you see here, and we use the Fick's law. So the total flow of concentration is minus K, some constant, dC dx. Then, identically, you can obtain the differential equation which represents this problem. It is d over dx, a multiplied by k, dc dx, that's equal to 0. In this case, for example, you can model the diffusing atoms with this differential equation. Certainly, for a given condition. Again, you take an infinitely small slice and you write the equilibrium condition. Certainly here, the Q is the number of diffusing atoms flowing through, or flux of diffusing atoms in this case. Therefore, multiplying it with the area will give you the total number of atoms that get into this tiny slice, and Qx plus delta x multiplied by Ax plus delta x will give you the total number of atoms which goes out from this tiny region, and therefore the net number of atoms will be this minus this one, and then if you divide it with delta x, you will arrive at this expression. Okay, so these are the strong forms. So how about the weak form? What is weak form? That's the thing. Now just consider an elastic problem again. We will just look at the problem purely in a mathematical sense in this case. Now I can choose a function w. W can be any function. As you see here, we have the for all w. And I can multiply my expression, my differential equation, with this w. So remember that the expression inside the parentheses is 0. So this is 0 already. So whatever I multiply it with, so it doesn't matter what the w is. If I multiply the w with 0, certainly I will get 0. And in fact, if I integrate this from 0 to L, certainly the value will be this integration, the result of this integration has to be equal to 0 as well. So this is one thing that we need to know. Okay, next we have the boundary conditions. Remember that at x is equal to 0, we have the traction force or traction, and it is a e du dx. So this is traction, and traction has to be equal to e du dx. And of course, this expression is 0. Whatever I'll multiply it with has to be equal to 0 as well. So for all w. Now here is the critical thing. On the right-hand side, I have the prescribed displacement. Now I choose a function. So I choose w in a manner that at the prescribed displacement or prescribed dependent variables in general, it has to be equal to 0. There are some exceptions, of course. Sometimes we enforce the displacement in the weak sense, but now this is out of our topic. But just consider that W has to satisfy this condition in order to be consistent. Okay, so now these are my conditions for the W. Now W is called weight function. Sorry. So it is weight function. Okay, now let's play with the expression. I just focus on this integral. So it is from 0 to L, w d over dx, a e du dx dx, plus 0 to L, wb dx, and that has to be equal to 0 for any function w. Okay. Now, of course, I want to get a better expression. Now, if I want to calculate this integral, first of all, I need to take the second derivative of the u. Remember that u is the dependent variable and x is the independent variable for our problem. And these two are the boundary conditions. So the traction and displacement is the boundary conditions. Let's go back. Yes. So this is our boundary condition, and this is our boundary condition, and this is our differential equation, which represents our problem. In fact, this type of boundary condition, because u is the dependent variable, this type of boundary condition is called Dirichlet boundary condition. And this type of boundary condition is called Neumann type of boundary condition because it's associated with the derivative of the displacement, derivative of the dependent variable. For example, in this problem, this is Neumann boundary condition. And this is called Dirichlet boundary condition because here I define the dependent variable. In this problem, T, temperature, is the dependent variable and X is the independent variable. Here, the boundary condition is associated with the derivative of the dependent variable. Therefore, this is called Neumann and this is called Dirichlet type boundary condition. Okay. Now, let's return back to how we obtain the weak form. Okay, now I have the weight function. I multiply my differential equation with weight function. Now, what I'm going to do is, let's look at the properties. Now, I have some function w and I have another function f. Here, in this case, f is this one. Okay, and d over dx wf. Now, certainly I have multiplication. Therefore, first I take multiply the first one with the derivative of the second expression, w df dx, and plus f multiplied by dw dx. Now, from here, I can write this expression, certainly, by just playing it. W df dx, if I take out the w df dx from here, I will arrive at this expression d over dx wf minus f multiplied by dw dx. Now, next thing is to integrate this expression from 0 to L. Now, if I integrate this expression from 0 to L, what I'm going to obtain is 0 to L d over dx wf dx minus 0 to L f dw dx. This will give me the formula for integration by parts. As you see, this is my expression. So w multiplied by df dx, integral of it, is equal to wf from 0 to L minus 0 to L f dw dx. In fact, I can write it like this because wf from 0 to L is wf at x is equal to L minus wf at x is equal to 0 minus 0 to L f dw dx. Now, if I use the integration by parts and apply it to this expression, this one, what I'm going to get is the expression below. Now, first, I take the first expression, then I take the second one. So this part, okay, W multiplied by AE du dx. So remember that this is equal to the sigma stress from 0 to L minus dW dx AE du dx. And the rest of the expression is the same because it's associated with the body forces. And not only because it's associated with the body forces, it doesn't contain any derivatives, and I cannot play on this integral anymore. So I arrive at this expression. This is my expression. This is my final form if I apply the integration by parts. When I look at this expression, the difference between the strong form and this expression is I only have first order derivatives. I don't have the second order derivative in this expression. And the condition is this: W, it is valid for any value of W where WL is 0. So, okay, but in this case, I need to define the boundary conditions. So remember that WL is equal to 0. Therefore, at WL, this function is equal to 0. And W0, for W0, this is equal to the stress. And stress is equal to the negative of the traction force. Okay. So let's continue further. I replace the E du dx with the stress value at x is equal to L minus WA sigma x is equal to 0. And then I have my integral from 0 to L dW dx, AE du dx, and so on. So remember that this expression is equal to 0. Because W is 0. By definition, because of our choice. Now, we are left with this boundary condition, which is on the left-hand side of my expression, WA sigma. And remember that this is equal to the traction T bar minus sigma is equal to T bar. Now I can take this body, this integral, to the other side of the expression, to the other side of the equation, equality, in fact, then I will be left with this final form. So from 0 to L, the W dx area multiplied with the Young modulus du dx, W area T bar, x is equal to 0 plus 0 to L WB dx for all value of for all W functions with WL is equal to 0. This is called the weak form. Now this represents the same problem, but in fact, in the weak sense, because we will see it much more clearly. So remember that what the difference between the derivative, just I want to tell you something. So the difference between the derivative and the integral is looking in the global sense. So here the strong form just consists of derivatives. Therefore, it enforces the problem to have a certain solution locally, but at each point. But certainly the weak form enforces the problem in the global sense. And it looks at the overall region because of this integration. So this is how you, this is the difference between the weak form and the strong form. Certainly we will see the difference much more clearly in the forthcoming classes. Now here, we need to know something about the functions. Now, from this point, we will get into, we need to talk about, mostly we will talk about the function and their properties. Now, one property is continuity. How we define the continuity by means continuity of a function in a mathematical sense. Now, just take any function f of x. We can define several different functions. Now, for example, here we show the continuity of a function by letter C. And 1, 0, minus 1 defines the how this continuity is happening, or how the continuity exists in this function. So if I say that, if, for example, if the function f is C1 continuous, C0 continuous, so what it means? Certainly, let's look at it. That's better. Now, for example, C1. What does 1 means here? The superscript 1 means. Now, superscript 1 means that the function is continuous and its derivative is also continuous. So this is why it is 1. In case of a C0 function, but certainly in case of a C1, its second derivative may not be continuous. So it may not be C2 continuous. Okay, so this is what it means. But if a function is C1 continuous, perhaps it is C0 continuous. What is C0? For example, a linear function. As you see, I have a piecewise linear function here. Okay, so the function is linear from here to here, as you see. And then the slope changes immediately, suddenly at this point. But again, it is the same function, but it is piecewise. The point is, this point is a kink. So what it means, the value of the function is continuous. It is C0 continuous. For example, if it is displacement is continuous, but its derivative is changing because the slope is changing here. So the slope in this range and in this range, in this region is different. This is C0 continuous. What else? Now C minus 1. What is minus 1 means? If you look at this function, okay, there is another function. Now, this function is piecewise linear. So the value of the function is constant in this region. And then suddenly it jumps to another value. And then again it's constant. Then again it jumps. Certainly these points are the jumps. And it is c minus 1. Because the value of the function is not continuous anymore. But you can integrate this function. So remember that the integration gives you the area under that function. And certainly I can calculate the area under this function. Look. So this is the area under this region, this is the area under this region, and this is the area under this region. So if I sum up, I can easily calculate these areas independently, separately, and then I can sum them up. This will give me the total area under this function, even though it's piecewise. And it's discontinuous, it has discontinuities. Now, why it is minus 1? Now, this is the point. So remember that d1 is the first derivative. Means that first derivative is continuous. And minus 1, you can integrate it. So you can integrate both functions, but minus 1 is due to the just taking the derivative, not the first derivative, but minus 1th derivative. So you say that this, while you are calculating the second derivative, you say that d square f dx square. How about d minus 1 f dx minus 1? That's the integration. So the integration is the inverse operator of the derivative. And this is why it is minus 1. Minus 1 represents that this function can be integrated, but you cannot take the derivative because there are certain points in which you cannot calculate the derivative. Derivative at these points are not defined. It is the same for the C0. You can integrate this function within the range, okay, within certain limits. But in fact, you can take the derivative within certain regions. The derivative exists, but there are points at which the derivative is not defined. So at this point, you have infinite number of derivatives, or it's not defined as well. But when you look at the C1 continuous, so the derivative is continuous. As a result, you can take the derivative of the function at any point. This is the thing about the continuity of a function.